Okay, this little video is about how to draw the graph of a derivative from the graph of a function, or vice versa. It is an experimental process in the beginning, so expect to make mistakes and have to redo it. I'm doing this on a Word document where I copied a Desmos graph in, and so I'm going to first take a look at my function. In this video, the functions are in red and the derivatives are in blue to help make that distinction. So I'm going to start by noticing that I have a maximum here and a minimum. And one of the nicest, most definitive things you can identify when you start to draw a derivative is the derivative zero anywhere? Do I have a horizontal tangent with a slope of zero anywhere? And maximums and minimums are perfect candidates. So I start by inserting a little marker where that zero would be. And here it looks like it's a little bit before 1. 2 boxes is 1 unit here. This is 0 and this is 2. So it's a little bit before 1. So I'm going to put a little X there. And I'm going to move it over because I think it's a little closer to 1. This is not an exact science, but we try to be as accurate as we can because we're developing an understanding of derivatives in doing this. So I have a derivative that's going to be 0 at the 2 locations, the 2 X values. One where I had a maximum at about 0.8 and one here where I have a minimum at about X equals about 3.7. And again, these are very nice because these are actually points that the derivative is going to go through. Furthermore, it can be very nice to insert a vertical line. It would go through the maximum and the X value where the maximum occurs, and similarly through the minimum and the X value where that occurs. This gives you a little wall. My derivative is 0. To the left of that wall, my derivative is positive. It's above the X-axis because my function is increasing. So my derivative is up here. And when I start to do these, I usually don't connect them up right away. I use whatever drawing tool I want, and I draw a part. I'm positive because my function's increasing, but I'm headed to 0 because I have a maximum here with a 0 tangent. You can even see that in the shape. I'm increasing steeply. That's why the values would be higher up here. But then I slow down. I increase more slowly until my rate of increase or decrease is 0. Okay, now between these 2 walls, my function is decreasing. So my derivative has to be down here. And I insert a shape down here that allows me to see that I'm negative, but I'm coming from 0, and I'm headed back to 0. Then on the other side of my wall, when X is greater than about 3.7, my function is increasing again. So I'm going to insert a placeholder for that increase. This may seem simple, but it isn't. And it's very good to have placeholders so that you don't draw something that's too extensive and then have to change it. This way, if any one of these pieces is wrong, I can delete just that piece. The same thing goes if you're drawing this with pencil. You just want parts, zeros, parts, zeros, parts, so you can connect them up, and if anything's wrong, just erase the part that's wrong. Notice that this kind of looks like it's going to be a parabola. And that does make sense because this looks like a cubic. And from what we know, the derivative of a cubic would be a second degree, a parabola. So I'm going to insert, I'm going to connect these shapes. I'm going to kind of draw over the whole thing again, not delete anything, just trace it. And I'm going to see that it's a little hard for me to keep to exactly what I had there. So then I go back and I delete pieces that get in the way, but that did guide me. They were very useful to have. So it looks a little odd the way I drew it, but you're not trying to go for a perfect shape. A true parabola might be centered differently, and you might want to do that again, but you don't need to. The idea is to simply understand approximately what the shape is. When the function is this red cubic, the derivative is going to look a little bit like this blue parabola. Now, I know what the equations are because I created the problem, and I just want you to see, I went into Desmos and got the graph of the actual parabola, and it is what you would expect. But again, you don't have to draw it perfectly. I didn't draw it perfectly. And you can expect to make mistakes and erase things. I still make mistakes and erase things. Okay, let's now do the second problem. In the second problem, this very same graph, the very same function, this is now the derivative. And I have to figure out what the function might look like. And I'm going to draw my function in red, but this tool isn't going to allow me to start it in red, so I will draw it in blue and then change its color. I hope that's clear. So what I have drawn ahead of time, and they're in red, I've marked out where my function might have maximums or minimums. This is the derivative, this blue graph. This blue graph is the derivative. So zero derivatives mean I might have a maximum or a minimum. I might have a maximum here. I might have a minimum here. The whole function might be positive or negative. I'm only looking for the shape. So I analyze what the derivative is telling me. These values here are negative. They're below the x-axis. So my function is decreasing here. Then there's this zero derivative, and then it's increasing. It's decreasing, and then it's increasing. It's decreasing, and then it's increasing. So I'm going to draw something that looks like that. Remember, decreasing doesn't mean it has to be negative. It's decreasing, and then it's increasing. That's part of it. Now I look over here, and this is going to be a maximum or a minimum. But I went from increasing to decreasing now. Increasing to decreasing. Positive derivative, I'm increasing until I get to this zero where it looks like it'll be a maximum because it's increasing to decreasing. So I continue. And again, I might be making a mistake. I'll just have to erase it and keep going. So I start from where I left off here. And I hit a little maximum. And now the derivative is negative, so I have to decrease. I don't have to decrease quickly, but I have to decrease. And I could decide to decrease until here, and then I have to start increasing again. And now if I want this to be red, I have to select red as the color because it's the function. Okay, so red is the original function and blue is the derivative. And look what's kind of interesting here. What's interesting here is that when blue is the derivative, and we thought this was a cubic, remember? If we go backwards to find the original function, that should be a fourth degree. And this kind of looks like a fourth degree because now we have two minimums and a maximum. We have an extra bump. Again, you may have to do this a couple of times, make many mistakes, and then you will suddenly see this connection. So let's look at the equations and what the actual original function looked like. I like to always compare to make sure that my sketch is good. Notice that this function actually is zero where it hits a minimum. I had no way of knowing that up here. but the general shape is the same. I have two minimums, one maximum. It's just I extend much lower than I thought, or than I chose. I had no way to know where this was. All I can get from the derivative is the shape, but that actually tells me a lot. The shape is the fundamental behavior of the function. Well, now you're going to try these, and you're going to work on them together, and you're going to discuss them, and you're going to laugh when you make a mistake, and then you're going to fix it.